This conference will now be recorded.
All right, this is a continuation of the 1.6 notes from class, and it's going to bleed into the 2.1 notes. So we're just hitting some extra examples that are very similar to each other so that when we get into class next time, we'll be able to jump right in to some of the more complex ones. So this is wanting to know, remember the directions for these, we're wanting to know which interval was this continuous on if it was a continuous function. And remember, sometimes they're continuous everywhere but a certain point or something like that. So when it's a piecewise function, I highly recommend graphing it. It's easier to see what you're looking at then. So this is 5 minus x only if we're using -1, 0, 1, or 2. And this one also would have another second function of x squared minus 1 if we're using 2 to 3. Now, I know that this is an open circle on the 2 here, but we do need to know what the value is as it gets closer to that. So if we plug in -1 here, that'd be 5 minus a -1. So that's actually 5 plus 1, so that's 6. 5 minus 0 is 5. 5 minus 1 is 4. And 5 minus 2 is 3. So we can plot those points. So -1, 6, and that's a closed circle because there was an equal to bar here. 0, 5 is just a regular point. 1, 4 is also just a regular point. And the other endpoint is 2, 3, and that is a closed circle for the end of that. So this is just a line kind of headed down to that. Now for x squared minus 1, at 2, that'd be 4 minus 1, so that's 3. And at 3, it's 9 minus 1 is 8. So 1, 2, 3, 4, 5, 6. I didn't have enough marks there, so that's up to 8. So the 2, 3 is the same. So even though this one is open because of this not having the equal to, because that one already is there and is closed, we leave it closed. And then the 3, 8 is a closed point because of the equal to, and this one's part of a parabola. Now the question is, if you go over this now, could you draw this without lifting a pencil? And the answer to that is yes. So this is continuous on its entire piece. Now, we actually, hang on just one second. We're going to leave those, I don't have an eraser here. We're actually going to leave those open usually because our definition of a continuous function is, remember, on an open interval. So by definition, we don't want to close those. We need to do a lot more work, and it's a lot harder to prove that it's on a closed interval, which means the brackets. So it is continuous from -1 to 3. Okay, we did the application problem in class, which leads us into the 2.1 problems, which is this stuff. And I did only one of these limits together. I wanted to do a harder one, and then I wanted to show you just some more limits, pretty much with the x squared and stuff like that, just some variety. So this is to find the slope of a secant line and have that turn into the slope of the tangent line. So the slope of a line at a specific point, which would be a tangent line, we need to look at the slope of a secant line as that delta x, or the difference between the 2 points, shrinks to nothing. So for this, we need to figure out what is x plus delta x and negative f of x. In this case, because that's an x cubed, I would probably do all of my work as scratch work, just because that is a little bit messy to cube out. Because we're going to have 4 times x plus delta x cubed, which means I'm going to go ahead and write it 3 times x plus delta x, and then minus the 2. So this is what we're working out when we put in the x plus delta x, we're cubing it. So we're going to have to FOIL these two together and then distribute this one as well. So 4x plus delta x, and then this is x squared plus 2x delta x plus delta x squared minus 2, because that's still not in the parentheses. We're going to distribute this x and plus delta x to this big piece right here. So that's going to be 4, and then we'll have x to the third. X times 2x delta x is a 2x squared delta x. Be careful to not combine the delta x with the x's. And then x times delta x squared is x delta x squared. And then we need to do delta x times everything. So we get another x squared delta x, a plus 2x delta x squared, and a plus delta x cubed, and then we still have our parentheses, and then the minus 2. So we're looking for any like terms inside here, and this is where things can get a little hard. This has an x squared, but a delta x is the first, and I believe we have another one of those. So yeah, 1 plus 2 would make 3 of those. So before I distribute that 4, I'm going to combine those like terms. So that's 3x squared delta x. I also have this guy, which is an x with a delta x, and I have another one that has 2x with a delta x squared. So notice x, delta x squared, that makes 3 of those. So that's squared. And then plus the delta x cubed, and then minus 2. So see, this one's really hard because this is all being cubed out, and it's a lot of steps. So we distribute the 4, and that will be it for that first part. And that's going to make all those 3's 12's. And then that'll be 4 delta x cubed. And then remember, that's just a minus 2. It was not in the parentheses. So notice that's just the top. So when we go to write our limit as delta x approaches 0, and that's just part of the top, by the way. We still have to do negative f of x, which is easy because we're just changing the sign of the function. So I'll go ahead and write that out. So this is going to be our big fraction bar here. And we have a 4x cubed plus a 12x squared delta x plus a 12x delta x squared. Those are not like terms because different things are being squared. Plus a 4 delta x cubed minus 2, and then this is the other one, minus 4x cubed plus 2 all over delta x. So my 4x cubes are going to cancel, so are my 2 and my negative 2. So that leaves me with the limit as delta x approaches 0 of 12x squared delta x plus 12x delta x squared plus 4 delta x cubed all over delta x. Now what's going to happen here is that, remember, some of those are going to cancel out, the delta x's. So when we reduce down, because everything has a delta x on top, we get 12x squared plus 12x delta x plus 4 delta x squared. Now your final step when you do this limit is you let, now that this has no dividing by 0 anymore because we got rid of the delta x in the bottom, we let all the delta x's become 0. So essentially they become 0. Okay, so that's going to make all of that go away, and this final answer is just 12x squared. Now remember, what this stands for is a formula, a generic formula for any time we want to find the slope of a tangent of a point on this function. We actually have a specific x value we want to plug in for that. So the slope of the tangent is going to be 12 times 1 squared, which is just going to be 12, and this is at x equals 1. So there's my slope of my tangent line at that specific point. Okay, let's look at some more. So we did the next one in class, so we're going to skip down to the next page. I'm going to save this one. I want to say we did it, but I can't remember, so I'm going to save that one for to talk about in class. And I'm just going to jump down and talk about a derivative for a second. We're going to pre-talk about this a little bit on this video, and then in class we'll do some, like I said, some harder ones of this. So the definition of a derivative is that the function that represents the slope of f of x, so remember that was what we just found, is called the derivative of f at x. It is denoted by, this is read as f prime. It's not an apostrophe, it's not a exponent, it's f prime of x. Or it can be denoted in what we call implicit form, which is dy dx. This says a function y taking a derivative in respect to x. So it's read as the derivative of y with respect to x. The process to find a derivative is called differentiation. So the way you find the derivative is just what we were doing. You're taking, so we actually have a name. So remember, slope of the tangent formula, this is our function we just found a minute ago, is found by doing this process of difference quotient and then letting the limit as delta x approaches 0 go to 0. So that is now called f prime. And that's only going to exist if the limit exists at that point. So a function is differentiable at x when its derivative exists at x. So for the first ones that we're going to do together on this video, all of them are going to exist because on the place we're at, because we're looking at for here on the video, we're looking at polynomials. And remember, they are continuous everywhere. So let's look at this very first one. So again, this is just the limit process. So the limit as delta x approaches 0, and I'm going to go ahead and do this as I go. So the x plus delta x is if I write the function above without the x's, and anywhere there was an x, there's now an x plus delta x. And then minus f of x just means change the signs of the function. So that's what my top would look like if I plugged it in without doing all the scratch work, since I didn't leave myself a lot of room for that. So then I need to FOIL out that top part and make any distributing. You get to a point where you've really memorized what x plus delta x squared is. It's always x squared plus 2x delta x plus delta x squared. Need to distribute that -5 minus x squared plus 5x all over delta x. And we're going to keep going. Things that cancel out, the x squareds and the -5x and the positive 5x. So that would just be 2x delta x plus delta x squared minus 5 delta x. Everything else on top canceled, so over delta x. And we're almost done with this one. So limit as delta x approaches 0, we reduce down all of the delta x's since there's all across the top. That one would just be -5. And notice there's only one of them that's going to end up turning into a 0. So this is just going to be 2x minus 5. Now remember what this stands for. This is called f prime of x. But what it means is that this is a function for the slope of a tangent line to f of x, our original function, at a point x. Okay? So let's do another one. This was just a typo. It said f of t. It should say f of x since this function is in x. So this one we're going to do the same thing. Now the hard part about these is that there's a lot of steps involved to cleaning it up, but it's not something we're going to do forever. So that always makes people happy when they find out you're not going to be doing these limits forever. We're going to actually teach you a shortcut in the next section so that some of these that are very simple you can do by just a rule. So yes, you're going to have to do one by definition on the test, which means doing the whole limit. But after that, we will rely on the rules. So you won't be doing this forever. So we're going to FOIL out that, and that's, remember, x squared plus 2x delta x plus delta x squared. We still have a distributed 3 plus 8 minus 3x squared minus 8 all over delta x. If I distribute the 3 on the top to that parentheses, that's 3x squared plus 6x delta x plus, my pen's not working. Hang on just a second. There we go. 6x delta x plus 3 delta x squared plus 8 minus 3x squared minus 8 all over delta x. And then what we want to do next is clean up the top. Some stuff's going to cancel. The 3x squareds are going to cancel, as are the 8 and -8. So that just leaves me with 6x delta x plus 3 delta x squared on top all over delta x. And again, the delta x's are canceling out all across the whole fraction, except there's going to be 1 left on that 3 since there were 2 on top. But when you let that go to 0, then you just get that this equals 6x. So f prime of x is 6x. All right, let me try to do one more, and that'll leave us just with some harder ones and one easy one that we can mimic in class together. So I'm going to do g of x right here. So the limit as delta x approaches 0, because remember that's how we find g prime, since this is a g function instead of f, is going to be 5 times x plus delta x plus 2 times x plus delta x squared minus 5x minus 2x squared, because that's the minus f of x part, all over delta x. So we're really just plugging into the same formula every time. So we distribute that 5. We're going to FOIL out the x plus delta x squared. So x squared plus 2x delta x plus delta x squared. Bring down everything else, all over delta x. We're going to distribute the 2. So that's going to be 2x squared plus 4x delta x plus 2 delta x squared minus 5x minus 2x squared, all over delta x. We have a 5x and a negative 5x. We have a negative 2x squared and a positive 2x squared. This one was a little bit out of order, so I kind of marked those this time. So I'm left with a 5 delta x plus a 4x delta x plus a 2 delta x squared on top, all over delta x. We reduce down all of our delta x symbols. And this would be 5 plus 4x plus 2 delta x. The delta x is going to go to 0, so that makes this whole term go away. So it's just 5 plus 4x. So g prime of x is 5 plus 4x. And like I said, we're doing these the long way, and then when we get to class on Tuesday, we'll do a couple more together, and then I'm going to teach you the shortcut, which will make you wish that you never had to do the long way. But in math, a lot of times you have to understand why things are working the way they are before we can just tell you memorize a formula. So that's it for this video. I will see you guys in class this week. At least we have 2 days, Tuesday and Thursday, and I hope you have a good Labor Day.